All right, hello. So here I'm just going to give a short introduction to differential operators, which were the main focus of the recitation yesterday. So today is October 14th, so this was October 13th's recitation. All right, so a differential operator is a polynomial that looks like this, where each of these d to the n, d to the n minus 1, all the way down to d, so d to the i's, are basically, so they're operators that are operating on variables, x, y, t, etc., that are sort of telling you to take the ith derivative of that variable. So here, d to the I means take the ith derivative. So you can sort of think of these polynomials as like instruction manuals on how to take derivatives or what derivatives to use in an equation. So for example, here, this equation here, so d squared minus 4d plus 3 of x, this would actually just be x double prime, where this term comes from d squared, minus 4 times x prime, where this term comes from 4d, plus 3x. And so here, 3 would just sort of correspond to the 0th derivative, or x term. So these operators have some nice properties. So notice, first off, we could have sort of alternatively broken up this sum, and so they're sort of additive in that way. So as an example, maybe I could have alternatively written this as like this. And gotten the same thing. Another nice property is that if I want to apply two operators, I can sort of apply them either by applying one operator then the other, or I can actually multiply the two and then apply them both at once. So I'll show you what I mean by that. So if we were to consider these two operators, L1 and L2, so you can see that L1 applied to x would just be x prime minus x. And so then L2 applied to that would be x double prime minus x prime. So that would be first derivative of this minus 3 times the original minus 3 times this, which is equal to x double prime minus 4x prime plus 3x. All right, so what we just calculated here, we calculated L2 applied to L1 applied to x. But notice L1 times L2 is actually just equal to d squared minus 4d plus 3. And so L1 times L2 applied to x is actually just the same. So this property is nice. We can kind of multiply them together in this way. And so for these reasons, we can sort of work with these things algebraically to help us solve systems of differential equations, as we'll see sort of here in an example. So why these are sometimes useful is if we have a system that looks like this, we can actually rewrite this system using differential operator notation. And then as we'll see, if we've sort of got a system that looks like the general form we're about to find, we can actually learn a lot from that. So what we're going to do is we're going to rewrite it in this form. So where L1, L2, L3, and L4 are differential operators, sort of telling us what order derivatives and sort of how those order derivatives should appear in each equation for x and y. F1 and F2 are just functions of t. So looking at this first equation, we know that L1 of x is equal to x prime minus x. So that would tell us that L1 should be equal to d minus 1. So first derivative of x minus 1 times x. And so we could sort of continue this process. I just have a 2y, so L2 would equal 2. L3, as it turns out, would also equal 2. And now I've got a 3y plus a y prime. So L4 would equal d plus 3. And now, looking at the right-hand side of each of these equations, F1 is equal to sine t, and F2 is equal to 0. So notice, using these operators, I was able to rewrite the equation in this form. So why is that useful? Well, ideally, to solve this, I'd like to use elimination or combine these two equations in such a way that maybe I can sort of eliminate either x or y and get an equation just in terms of y and t, or just in terms of x and t. Reason being, once I've done that, we can apply sort of previous methods that we know, for example, undetermined coefficients, to solve that equation for either y or x in terms of t, and then go back and solve for the other variable. All right, so how are we going to do this? So I'm going to call this equation 1 and that equation 2. And I'm going to calculate, I want to make sure I get this right, L1 times equation 1, sorry, L1 times equation 2 minus L3 times equation 1. All right, so I'm going to have two equations here. So I've got L1 times equation 2, which is L1, L3, plus L1, L4 of y equals L1, F2 of t. And so remember, each of these L's are just instructions for how to take derivatives. And so we can sort of, as long as we take the same derivative and combine the same derivatives of each equation in the same way on each side, then we don't lose equality. From this, we're going to subtract L3 times equation 1 plus L3 L2y equals L3 F2 of t. We're going to subtract that whole thing. All right, so remember, operators are just instructions how to take derivatives. It actually doesn't matter what order we take those derivatives in. So that means L1, L3x, L3, L1x are actually just the same thing. And so when I subtract these two equations, those cancel out. So I'm left with L1, L4 minus L2, L3. And so again, just to reorder these, it doesn't matter which order I take these in, applied to y, is equal to, and this should be F1 here, L1 F2 of t minus L3 F1 of t. And so notice I've used equations 1 and 2 to now calculate a differential equation in terms of just y and t. So remember, these are just complicated instructions for how to take derivatives, and we'll sort of apply this to this example to get a more concrete idea of what this is going to look like. These are just functions of t with some derivatives having been taken. And so if we were to actually expand this and apply all these operators, we'd get a differential equation. So let's try that. So let's see. I think what I'm going to do is I'm going to erase this for now, just to give myself a little more room. All right. So L1, remember, was d minus 1. Times L4, which is d plus 3, minus 2 times 2, applied to y, equals L1 is d minus 1, F2 of t is just 0, minus L3, which is 2, times F1, which was sine t. All right. So if we expand this polynomial on the left, you should get d squared plus 2d minus 7 applied to y is equal to negative 2 sine t. And now remember, this was just an instruction manual for what derivatives of y should appear in our differential equation. So this tells me that y double prime plus 2y prime minus 7y is equal to negative 2 sine t. And so certainly if I was solving the differential equation, I wouldn't stop there. But this is now something we can solve. So on the left, you could find a complementary solution to the associated homogeneous equation, and then you could find a particular solution. So this would just be method of undetermined coefficients to solve this. And so I don't want to take all the fun away from you. So I'll let you solve this for a little more practice. Yeah. So what if we'd wanted to start with x? Well, we could have alternatively done that. So notice here, if we had any general equation written in this form, and so notice this was an example where we sort of wrote this equation in this form, but if we had sort of just an equation that we could write in this form, or system of equations, I guess I should say, that we could write in this form, we could have alternatively done the following. So we could do L4 times equation 1 minus L2 times equation 2. So that would get us L4, L1 applied to x plus L4, L2 applied to y. And so that's equal to L4, F1 of t. Now we're subtracting off L2, L3 applied to x plus L2, L4 applied to y, and that's equal to L2, F2 of t. And notice what this gets us, and I'll move the answer down here just for space. So the difference of L4 times 1 minus L2 times 2, this actually gets us L1, L4 minus L2, L3 applied to x is equal to L4, F1 of t minus L2, F2 of t. And so much in the same way, had we gone this direction, we could have gotten a differential equation in terms of x and t, and then just solved it. So a few important things to note about this. So I'll erase this and this. So notice that the left-hand side of each of these equations is actually the same. And this, as it turns out, is not a coincidence. So the left-hand side of these equations, and so ignoring x and y, so just this piece here, is called the operational determinant of this system. And so the operational determinant is actually just the determinant of this matrix, L1, L2, L3, L4, which, as it turns out, is the difference of the cross products. And so this is just the operational determinant. So from the operational determinant, we can actually learn a lot about the system of equations. And so I want to talk about just one of the things now. However, there's a lot more that we can learn beyond what the one thing that I'm going to introduce. So from the operational determinant, we can actually know how many. So fact, the order of the operational determinant, or I guess I should say maybe not the order, the degree. The order, you might also think of it as the degree of the operational determinant tells us the number of arbitrary constants in a solution. So what does that mean? Well, in the example I just erased, so previous example. So remember this, so L1, L4 minus L2, L3, the operational determinant, which I'll just shorten as opdet, was d squared plus 2d minus 7, I believe. Let me double check that before I go making wild and crazy claims. Yeah, d squared plus 2d minus 7. So the order or degree of this polynomial is just the highest degree term in this polynomial. So we'd say the order is 2. And so this would mean there are 2 arbitrary constants in a solution. So that's kind of nice. Just from, if we've got a system that looks like this, just from looking at now this operational determinant, we can figure out how many arbitrary constants are going to exist in a general solution to this system of equations. So the determinant can actually tell you a lot more, which I won't go over in this video, but I'd highly recommend looking up in the book. It turns out, so this fact only holds if the operational determinant is non-zero. I should point that out. So if the opdet is not equal to 0. If the operational determinant is 0, then it actually turns out that this system sort of splits into two cases where either there's going to be infinitely many solutions to one of these systems, or there's going to be no solution, no possible solution to this system. And so in that case, if the operational determinant is 0, you would say this system is degenerate. So I want to actually end this by going over one more example that is related to a previous homework problem. So this was homework 9, question 10. I just want to quickly review one more example of sort of how we'd use this on a system that maybe has a little more going on. All right. So we're given the following system. All right, and so first we want to calculate the operational determinant and actually use that to figure out how many arbitrary constants are going to appear in a general solution to this. And then we're actually going to go ahead and calculate the general solution. So remember, we want something that is in this form. Naturally, of course, I erased it. Is equal to f1 of t. All right. So I just want to now figure out what is L1, L2, L3, and L4. And usually, with this problem at least, it's a little more straightforward to figure out, I guess. And so remember, the opdet is equal to L1, L4 minus L2, L3. So this would be d squared plus 2 times d squared minus d squared plus 4 times d squared minus 2. All right, fun algebra time now. So this is equal to d to the 4th plus 2d squared minus d to the 4th plus 2d squared minus 8. And almost too conveniently, the operational determinant is equal to 8. All right, so operational determinant, is equal to 8. What does that tell us? Well, that tells us, so the order of the operational determinant is the highest power of d that appears in the polynomial, which here the highest power of d that appears in the polynomial 8 is just 0. And so this means there will be no arbitrary constants in a general solution. Cool. So we'll actually see kind of why in a second, that when we actually go to calculate the general solution, this fact will make it relatively easy for us. But so let's keep this in mind. No arbitrary constant in a general solution. Now we just have to find that general solution. So if you'll remember, and once again, I probably erased these a little too soon. The two equations we derived from this were the following. And I should probably check so that I don't accidentally get them wrong. So there is if we wanted to solve for y, and if we want to solve for x. We should get this equation. So remember, this was combining these two equations in order to eliminate either y or x. And so first, solving for y. Well, remember L1, L4 minus L2, L3, the operational determinant was just 8. So the left side of this first equation would just be 8y. This is equal to L1 times F2, but notice F2 is 0. So this would just be negative L3, which is d squared minus 2, applied to 40e to the negative t. What was d squared minus 2 telling us to do again? Yeah, that's right. D squared minus 2 was just telling us to take the second derivative of this and subtract off 2 times this. Well, it actually turns out the second derivative of 40e to the negative t is just 40e to the negative t. Negative 2 times this is negative 80e to the negative t. So we get 8y is equal to positive 40e to the negative t, once I subtract and cancel out a negative, and y is equal to 5e to the negative t. All right, so now we can do something identical for x. L4, F1, so that should be just the second derivative of 40e to the negative t. Notice again, F2 is 0. Second derivative of 40e to the negative t is just itself. And x is equal to 5e to the negative t. So you can see, starting with something like this, using this notation, how useful this can be. We can sort of just combine these in such a way to get these solutions. So that wraps up what I had planned for this video. Mostly, like I said, I kind of just wanted to introduce this notation, go over it a little bit, and go over how the operational determinant can help us. So yeah. So again, feel free to email me if you have any questions, and thanks for watching.